This video, we're going to talk about linear independence of a set of functions. This is going to be from textbook section 4.1.2. We're going to be looking at problems 15 through 21 odd. Our first example here is going to be f1 of x is equal to x, f2 of x is equal to x squared, f3 of x is equal to 4x minus 3x squared. Now, if I can find coefficients C1, C2, and C3 not all 0, so that this equation that I just wrote is true, where I can make them equal to 0, then they are linearly dependent. If the only solution to this equation is C1, C2, C3, all the constants in front of the functions have to be 0, only that trivial solution exists to give this equal to 0, then they're linearly independent. So these are linearly dependent because we can see that 4f1 minus 3f2 is equal to f3. So 4f1 minus 3f2 minus f3 is going to be equal to 0. So I have C1 equals 4, C2 equals -3, C3 equals -1. So they are linearly dependent. Let's go ahead and look at 17. And I have f1 of x is equal to 5, f2 of x is equal to cosine squared x, f3 of x is equal to sine squared x, because I know that sine squared x plus cosine squared x is equal to 1. I can have 5 sine squared x plus 5 cosine squared x is equal to 5. So 5 times f3 plus 5 times f2 is equal to f1. So a negative f1 plus 5f2 plus 5f3 is equal to 0. C1 is equal to -1, C2 is equal to 5, C3 is equal to 5, and they are linearly dependent. All right, let's move on to number 19. F of x is equal to x. F1 of x, F2 of x is x minus 1. F3 of x is x plus 3. So let's try this here and see if we can take C1 times x plus C2 times x minus 1 plus C3 times x plus 3, get it equal to 0. That means that for my x's, C1 plus C2 plus C3 has to be equal to 0, and negative C2 plus 3 C3 has to be equal to 0. So that means that C1 plus 4 C3 has to be equal to 0, and that C1 has to be -4 C3. So the only way that that's going to happen to get, let's try that. Let's just stick a number in here. Let's let C3 equal to 1. That means C1 is equal to -4. So we have -4x. And then we have C3 is 1. We have x plus 3. So that's going to be a negative 3x plus 3. If I multiply, let's see, if we have C2 is equal to 3, then we get 3x minus 3, and they're not all 0. Any of them could be 0, but in this case, none of them are 0, but they're not all 0, so these are dependent as well. So let's go ahead and look at number 21 here, will be our last one. F1 of x is equal to 1 plus x. F2 of x is equal to x. F3 of x is equal to x squared. Some of you may have been asking just a minute ago why I didn't use a technique called the Wronskian to prove this dependence or independence idea. It's just not taught yet in the book. It'll come up in later chapters, especially when we do variation of parameters later on, but it's just not a technique. Your teacher may introduce it at this point. And if so, go ahead and use the Wronskian to prove independence. But let's go ahead and see if C1 times 1 plus x plus C2x plus C3 x squared is equal to 0. Well, I know C3 is going to have to be 0 because I don't have any x squareds over there. There's nothing over here to balance this out. So now if I try and make C1 and C2 opposites, so the x terms cancel each other out, I'm still going to be left with a constant from C1 here. I'll show you that. So if I have C1 plus C2 equals 0, and C1 has to be equal to 0 because there's no constant over here other than 0. Then if C1 is 0, C2 also has to be 0. They're all 0. So this is independent. All right. That is it for this video. We'll come back next time and look at 4.1.3 non-homogeneous equations. And I'll see you for the next video.